In topic 2.5, we want to focus on how to take the derivative of what we call power functions. And so let's define what a power function is, and then let's use our limit definition to take a derivative of a power function and then see if we maybe can't see the pattern that's going to emerge in something that we're going to, in the next video, define as what we call the power rule for taking derivatives. So just to kind of define what we mean when we say a power function. A power function is a function that takes the form of f of x equals kx to the p. And so that's a lowercase p there, kx to the p. And we do define k, which is, for what it's worth, the coefficient in front of x, and p, which is the power or exponent being applied to x. We do define both of those as being real numbers. And so, for example, if I gave you the function f of x equals 4x cubed, that would be a power function where 4 would be the coefficient, 3 would be the power. And so that's what we mean when we talk about power functions, just very simple functions where x has a power being applied to it and may or may not have a coefficient. And in fact, today we're going to focus on functions where the coefficient is actually 1. In the next topic, we'll bring in what to do when there's a coefficient outside of one of these power functions. So let's use our limit definition, which is the only thing we know to take a derivative right now. Let's use the limit definition to take the derivative of f of x equal to x cubed. And so again, I'm letting my coefficient here be 1 for today. We'll bring in coefficients in the next topic, but it is a power function. X is being raised to a power. In this case, the power is 3. It's just your parent cubic function. So I'm going to use the limit definition here to take the derivative. And as I'm doing it, I really encourage you to watch what's happening, because something happens whenever we talk about these power functions that when I take its derivative is always going to happen. And so we can kind of apply a very convenient rule once we see what the pattern is. So just a reminder, f prime of x, the derivative of x, is going to equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. There's our limit definition of derivative. And just as I've done in the past, I'm going to do a little bit of bookkeeping off to the side because I need to know what f of x plus h is, and I need to know what f of x is. Well, f of x plus h, well, let's start with f of x. F of x is x cubed. We already know that. F of x plus h is going to be x plus h, quantity cubed. And I will tell you, I'm going to go ahead and give this to you. You could multiply x plus h times itself and then multiply it by x plus h again. There's actually a formula. It's very formulaic. If you take a binomial, in this case x plus h, and raise it to any power, there actually is a method that allows you to find what that is very quickly. And so I'm going to tell you x plus h to the third power is x cubed plus 3x squared h plus 3xh squared plus h cubed. And as we kind of take note of what's going to be happening here as we find the derivative, the fact that I mentioned earlier, this is a pattern that if I took x plus h and I raised it to the 7th power, I actually could come up with each term, instead of having to multiply it out 7 times, it actually is formulaic writing it out as an expansion like this. And that's actually going to be really important here in a moment when we want to apply the pattern we think we see to kind of the general power rule. So let's take this derivative, and then once we've got it, let's take a look at the result and see what happened and see if we can't see the pattern that's going to emerge. So this is the limit as h approaches 0 of f of x plus h, which we said was x cubed plus 3x squared h plus 3xh squared plus h cubed minus f of x, which was x cubed, and it is all over h. Now then, as we've worked with this limit definition of the derivative, we're kind of aware of the fact that everything without an h should cancel off, and in fact the x cubed and the negative x cubed do cancel each other out. So I'm left with the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed, and that's all over h. Well, now that everything has an h in common, I can divide off that h, which is what I want to be able to do to evaluate the limit, is I need to divide out what's making the denominator 0. So I get the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Well, now I know to evaluate this, I can just substitute 0 in for h. So I get 3x squared plus 3x times 0 plus 0 squared, which is simply 3x squared. And so I can say for f of x equal to x cubed, just our parent cubic function, f prime of x is equal to 3x squared. So if I look at this, look at what I started with. I started with x cubed, and I ended up with just a single term derivative that happened to be 3x squared. So let's go back and revisit up here in my little bookkeeping to see what survived this process. I knew when I took f of x plus h and I cubed x plus h that I got this long term right here. And in fact, I need to be able to do this to any power. So one of the things that happens when you take a binomial and you raise it to a power is, so for example, if this said x plus h to the 7th power, my first term is always x to the power. So if this were x plus h to the 7th, it would be x to the 7th power. I also know it would end with h to whatever power. And in between what happens, so for example, if this were x plus h to the 7th, I would start with x to the 7th, I would end with h to the 7th. And what happens is, every term, the power of x decreases by 1, while the power of h increases by 1. So I could really envision this first term as x cubed h to the 0, and then the next one is x squared h to the 1st, then x to the 1st h to the 2nd, followed by what would be x to the 0 h cubed. That pattern happens regardless of what this exponent is. So every single time that I have a term, the power of x decreases by 1, while the power of h increases by 1. Now then, if you think about what survived the derivative process, the x cubed was always going to subtract off with this. So for example, if this were x plus h to the 7th, this x to the 7th would subtract off with this x to the 7th. So this guy right here never survives this process. The other thing that happens, because I have just a single term of h in the denominator, is that everything that has h to a power larger than 1, this term with h squared, this term with h cubed, and again I could apply this in a more general sense, but anything with a power of h larger than 1 still has an h left over whenever it gets divided off, which means when I substituted 0 in for h, that whole term got zeroed out or wiped out. So the only part of this that was ever going to survive the derivative process was this second term right here. It survived because it didn't subtract off anything up here, and because it only canceled out that single h, it was the part that was left over whenever we substituted 0 in for h. So let's talk about where this second term comes from. We already said that it decreases the power of x by 1. So for example, if I had x plus h to the 7th, this term right here would be x to the 6th h to the 1, which means it would survive this derivative process, and I would have x to the 6th as kind of the main idea. The next question is, where does the coefficient come from? It just so happens that, I mentioned earlier this was formulaic in nature, it just so happens that the second term right here, its coefficient is always whatever the exponent is. So there's a huge pattern that works here where I can say, hey, the coefficient of this term right here is always the exponent, and it always decreases the power of x by 1. And that's the part that survives, and that's actually going to be the rule that we're able to kind of focus in on and establish for taking derivatives. So what we're going to do next, and really the heart of this topic explores the relationship between a power function, and again, we're going to let the coefficient be 1 for today. We'll add in coefficients in the next topic. So we're going to explore the relationship between a power function and its derivative. And it really is going to be as simple. If we have a function like x to the third, hopefully you can see where this 3 comes from, and hopefully you also can see where the power gets reduced by 1 if you understood what was happening here with this limit definition. So we can write a very simple and easy to follow rule if we understand the relationship between the function and its derivative and understand what happened with this process right here.